let's look at how to add vectors. We will start with a geometric interpretation in 2 dimensions. So to illustrate this, let's start with 2 vectors. Vector x is the vector that goes over 4 and down 3, and vector y is the vector that goes over 1 and then up 5. Now remember that vectors don't typically have a spatial location, so we can actually move vector y so that it lies right there. Now this we call laying the vectors heel to toe. Okay, the heel of y, where y starts, is now where x ends, which is the toe of x. Now, if one went in the direction of x and then in the direction of y, then the net result would be that one would go from the heel of x to the toe of y. So that gives us the black vector. And the black vector is what we call x plus y. So x plus y is adding these 2 vectors together. But notice that for the first component of x plus y, we went to the right 4 units and then to the right 1 more unit. So the net effect was that we went to the right 4 plus 1 units. And then we went down 3 units, followed by up by 5 units. So the net effect is that we went up by 2 units. So the result of adding x to y in this case is the vector 5 to the right and then up 2. Now, we could have instead followed vector y first and then followed vector x, and we would expect to end up at the same place. So we can lay vector x heel to toe with vector y and end up with the same vector, which is this black vector right here, which is then y plus x. Now we can summarize this with the following observation. If you lay y heel to toe with x, or you lay x heel to toe with y, you end up in the same position. That creates this parallelogram that you see here. And then the result of adding x to y or y to x is this diagonal of the parallelogram. And that's known as the parallelogram method. So what if we wanted to add 2 vectors of arbitrary size? Well, if we want to do x plus y, when we can look at the components of x and y individually and recognize that corresponding components then need to be added. The general geometric interpretation is that if you look at 2 vectors x and y, they actually lie in a plane, as we will see much later in the course. And if we then view them in that plane, then the result of doing x plus y is exactly as we saw it before. Or we can go in the direction of y first, and then in the direction of x. Now, if we wanted an algorithm for computing the result vector z that results from adding x to y, then we can expose the components of z, the components of x and y, and we recognize that the ith component of z just equals to the sum of the ith components of x and y. And we can then summarize that as a little loop that says for all components of z, for I from 0 to n minus 1, the ith component of z, zeta sub I, should just be computed as chi sub I added to psi sub I. So to summarize, it's very important to remember and understand this parallelogram right here, and to recognize that if you add 2 vectors together, you simply add the corresponding components.